What is the cause of a mechanism associated with lightning strikes? How do lightning rods serve to protect buildings from the devastating effects of a lightning strike? It all started with the static charge build-up in the clouds. The precursor of any lightning strike is the polarization of positive and negative charges within the storm cloud. The tops of the storm clouds are known to acquire an excess of positive charge, and the bottoms of the storm clouds acquire an excess of negative charge. Two mechanisms seem important to the polarization process. One mechanism involves a separation of charge by a process that bears resemblance to frictional charging. Clouds are known to contain countless millions of suspended water droplets and ice particles, moving and whirling about in turbulent fashion. Additional water from the ground evaporates, rises upward, and forms clusters of droplets as it approaches a cloud. This upwardly rising moisture collides with the water droplets within the clouds. In the collisions, electrons are ripped off the rising droplets, causing the separation of negative electrons from positively charged water droplet or a cluster of droplets. The second mechanism that contributes to the polarization of a storm cloud involves a freezing process. Rising moisture encounters cooler temperatures at higher altitudes. These cooler temperatures cause a cluster of water droplets to undergo freezing. The frozen particles tend to cluster more tightly together and form the central regions of a cluster of droplets. The frozen portion of the cluster of rising moisture becomes negatively charged, and the outer droplets acquire a positive charge. Air currents within the clouds can rip the outer portions of the cluster and carry them upward toward the top of the clouds. The frozen portion of the droplets with negative charge tends to gravitate towards the bottom of the storm clouds. Thus, the clouds become further polarized. A lightning bolt begins with the development of step leader. Excess electrons on the bottom of the cloud begin journeying through the conducting air to the ground at speeds up to 60 miles per second. These electrons follow zigzag paths towards the ground, branching at various locations. The variables that affect the details of the actual pathway are not well known. It is believed that the presence of impurities or dust particles in various parts of the air might create regions between clouds and Earth that are more conductive than other regions. As the step leader grows, it might be illuminated by the purplish glow that is characteristic of ionized air molecules. Nonetheless, the step leader is not actual lightning strike. It merely provides the roadway between the cloud and Earth along which lightning bolt will eventually travel.
Lightning is a high current electrical discharge in the atmosphere. Thunderclouds are the most common producers. For this discharge to occur, there must be a charge separation large enough within the cloud to cause electrical breakdown of the air. Thunderclouds generally develop a high negative charge at their base, while the ground is positive relative to the cloud. When this large potential difference is discharged, the result is lightning. A lightning stroke begins with an invisible discharge called a step leader, which moves downward in discrete steps. As the negative leader approaches the ground, another leader moves up to meet it. When the two make contact, visible lightning, called the return stroke, instantaneously propagates upward from the ground along the path of the leaders. Subsequent strokes will occur until the charge center in the cloud is dissipated.
As electrons on the step leader approach to the Earth, there is an additional repulsion of the electrons downward from Earth's surface. the quantity of positive charge residing on the Earth's surface becomes even greater. This charge begins to migrate upward through the buildings, trees, and people into the air. This upward rising positive charge, known as steamer, approaches the step leader in the air above the surface of the Earth. The steamer might meet the leader at an altitude equivalent to the length of a football field. Once contact is made between the steamer and the leader, a complete conducting pathway is mapped out and the lightning begins. The contact point between the ground charge and cloud charge rapidly ascends upward at speeds as high as 50,000 miles per second. As many as 1 billion trillion electrons can traverse this path in less than a millisecond. This initial strike is followed by several secondary strikes of charge surges in rapid succession. These secondary surges are spaced apart so closely in time that it may appear as a single strike. The enormous and rapid flow of charge along this pathway between the cloud and the Earth hits the surrounding air, causing it to expand violently. The expansion of the air creates a shockwave that we observe as thunder.
Yeah, that just hit the light bulb right there. Yeah.
I got that first one. Whoa! Whoa! I got that! I recorded it!
Lightning is the discharging of electricity, usually in the midst of mature thunderstorms. It can be inside a cloud, from one cloud to another, from cloud to air, or cloud to ground. Cloud to ground lightning occurs when there is an electric potential gradient inside the cloud that causes electrons to discharge towards the ground. Negative cloud-to-ground lightning occurs when the stroke carries negative charges from the cloud to the ground. This is the most common. 90% of all lightning is cloud-to-ground lightning. Most lightning strokes are negative strokes, meaning that they have a large concentration of negative charge in the cloud base and a concentration of positive charge on the ground. Positive cloud-to-ground lightning occurs when the base of the cloud is positively charged and the ground negatively charged. Positive strokes are most common in severe thunderstorms just prior to tornado formation.
Some time back, an article in Wind Power Engineering Development said that lightning bolts carried almost 5,000 amperes to 200,000 amperes, and voltages vary from 40,000 volts to 120,000 volts. So if we take some averages, say 100,000 amperes and 100,000 volts, these bolts will carry this much power. There is uncertainty that there might be like 10,000 times 10 to the 6 watts in the air. Now let's assume that this energy is released in just 1 second. So the power gives 10 to the 10 watts a second. We can use this information just to know how many energy would it be needed from a bolt to give light to energy to a whole town. First, we have to ask ourselves, how much power does a single house consume? Then we need to play with the average, and let's assume that a house needs like 2000 watts per hour to keep the fridge, the furnaces, the computers, the television, the light bulbs, anything that needs energy. And one day has 24 hours. The house can consume for over 48,000 watts per hour. So if we divide the power drawn to the house into the power of a lightning bolt, we'll have that houses half that bolt can power. Now we have that a bolt can give 2.7 times 10 to the 6 watts hour. And a house to work needs 4 times 10 to the 4 watts per hour. We make our division, we see that around 56 houses can be fit up with one single bolt in a day. So the answer to the original question is that a big bolt could power a small quantity of 55 houses for just one day. That says that the amount of energy that bolts can give is huge, is gigantic. Just 55 houses with one single bolt per day. And let's say that millions of bolts are given in one single lightning storm. A bolt is a huge amount of energy, and that implies that carries a lot of danger, so some protective measures need to be taken care of. And they have been, like buildings, tall buildings and farmhouses are susceptible to lightning strikes, and often are equipped with lightning rods. These lightning rods are attached to the ground from the building in order for the bolt, follow that path to the ground and do nothing to the structure of the building or to the people that are in it. This concept of lightning rod was originally developed by Benjamin Franklin. Benjamin Franklin proposed that lightning rods should consist of a pointed metal pole that extends upward above the building, and it is intended to protect the building. He suggested that the lightning rod protects the building by one or two methods. The first method says the rod serves to prevent a charged cloud from releasing a bolt of lightning. And the second one, the lightning rod serves to safely divert the lightning to the ground, like I said earlier. in the event that that cloud does discharge its lightning via bolts. Other ways that you can prevent it: if you are in a lightning storm and you're in your car, you need to sit inside your car. It doesn't have a lightning rod, but it has the tires, which its material will serve to give the lightning over the ground without entering into the car. Another reason why you shouldn't get off the car is because it works as a Faraday cage. What is a Faraday cage? When you see the lightning, it's just trying to reach the safest, not the safest, the easiest way from getting from the cloud to the ground. Now, cars are built with metal, with steel. And you would say, why would I stay in my car, otherwise in tires? If it is made of steel, the lightning would definitely go to the car because it is made of steel. Well, because of it, the lightning is just series of electrons that are trying to get from one place to the other, from the cloud to the ground. And the Faraday cage is a concept, it's not an actual cage. It's a concept that says that the lightning would hit into the cage, the electrons will follow the seal of the cage to the end of it, which is the ground, without touching the inside. So if you stay in the car, it would work as a Faraday cage because it is made out of steel. It would go all over the car without getting in and get to the tires, and from the tires it will go to the ground.